So, a very good afternoon to all, and welcome to the new class of solution. I hope my voice and my screen is visible to you all. Yeah. So, in previous class, we are solving some numerical, which was based on the Rawls law and the molality and molarity, right? From today, we are going to start colligative property, and this one is very important topic of this chapter, that is solution, right? So, try to understand this topic, try to understand the concept behind this, because colligative properties play a very important role. A very large number of many questions were directly coming from this topic only. So this is totally numerical based topic. But before doing numerical, you must know the concept behind this. What do you mean by colligative properties? What are their importance? Where we use colligative properties? What are the significance of colligative properties? Right. So let's start with the today's session. I hope all of you join the class. Okay, so let's start with the today's session. This question I'm giving yesterday for your homework. I hope you all did this question. Anyone having any kind of doubt related to this question, you can ask better, right? Okay, let me solve this question once again. Okay, so that if you have any doubt related to this question, it will be automatically get cleared, right? So, yes, join us. Now, this question states that the vapor pressure of the two liquid, that is P and Q, are 80 and 60 torr respectively. Now, the total vapor pressure of the solution obtained by mixing 3 mole of P and 2 mole of Q would be. So, you have to calculate the total vapor pressure. So, what we learned so far, beta, to calculate the total pressure if you mix two liquids, we all know what we know, beta. We know that now we calculate total pressure by just adding PT is nothing but is equal to P1 plus P2, right? And what is this P1 plus P2? P1 plus P2 is nothing but P naught 1 into X1 plus P naught 2 into X2. So this is all about this P1 X1 and P2 X2, right? Okay. So in this question, the vapor pressure of the two liquids P and Q are already given. That is in pure state, the vapor pressure of P1, that is P is given 80 and Q is given 60. Now you have to calculate the mole fraction of individual, right? X1 and X2. And when you calculate the mole fraction, then you get the answer of this question. So it is a very simple questions. And it also, come in our AIMS 2012 examination. So let's calculate the mole fraction of individual. So if I want to calculate the mole fraction of X1 here means P, right? And X2 means here Q. So X1, so what is the mole fraction of X1, beta? So it is nothing but 3 divided by total number of moles, that is 3 plus 2. So it comes out to be 3 by 5. Okay. On the similar basis, what is X2, beta? That comes out to be 2, 3 plus 2. So it will be 2 by 5. So this is the mole fraction. Now we know what is P1. So P1 is nothing but 80. So just multiply 80 by 3 by 5 plus 60 into 2 by 5. What will get, beta? क्या मिला हम सबको जल्दी बताओ. You'll cancel out each other now. That is 5 16 and 5 से 60 cancel कर दो, right? So 12 5 so 60, right? So this is 12. This comes out to be 16 into 3, 48 plus 12 into 2, 24. So just add these two, you'll get 72 torr. So this is the correct answer for this question. So the correct option is D. So I hope this is clear to you. It is very easy question and it is totally based upon the Rawls law. Because in Rawls law only we get to know how to calculate the total pressure when we mix two liquid having vapor pressure in their pure state. So it states that the total pressure is nothing but it is equal to the partial pressure of the individual liquids, right? So this is the correct answer, that is 72 torr. Now, From today, we are going to start a very, very important topic, that is colligative properties. To try to learn this topic and try to, understand this topic, what the colligative properties actually are and why they are so important, that many time questions were directly coming from this topic, right? So let's understand this topic, right? Okay, so first of all, what is colligative property? Basically, colligative properties are the properties of dilute solution. So colligative properties are basically used for dilute solution, which depends only upon the number of only depends upon the number of solute particle and independent of their nature, size, and all. Right. So colligative properties are those properties which depend only on the number of solute, or we say number of solute particle, and is entirely independent of its nature, shape, size, and their chemical nature. So they are entirely independent. So it is very simple to remember what is colligative property. Right. Okay. Just remember one thing. It depends only on the number of solute. Okay. For example, let me explain with this with a certain example. If I'm talking about, we have 1 molar glucose, right? 1 molar glucose solution, or we say we have 1 mole cane sugar, right? This is cane sugar. We all know glucose and cane sugar are two different physical things, right? Glucose has a different function, where the cane sugar has a different function. Glucose having the different molecular formula, cane sugar also having different molecular formula. But here, what the common is, both having 1 mole or 1 mole. So we know that 1 mole is equal to how much, beta? 1 mole is equal to 6.023 into 10 raised to the power 23 atoms or molecules or ion, right? Atoms, molecules or ion. So in this, if I'm talking about the colligative properties of glucose and cane sugar, it comes out to be same. Why? Because the number of particles remain same here. Because 1 mole of glucose also contains this much of atom, molecules or ion of glucose, and 1 mole of cane sugar also contains this much atom or molecules or ion of glucose cane sugar. Right. So here the number of particles remain same. It means if I'm talking about the colligative properties of both glucose and cane sugar, they comes out to be same, right? Whereas if I'm talking about we have a 2 molar glucose and 1 molar glucose. So here both in both cases glucose are present. But if I'm talking about the colligative properties, then 2 molar glucose having a greater colligative properties as compared to 1 molar glucose, because in the 2 molar suddenly number of atom, molecules, ion is increases. And if the number of solute particle increases, then colligative properties also increase, right? And if the number of particle remains the same, whether if I'm talking about the two different physical quantities or two different or same things, if the number of quantities increase, then their colligative properties increases. And if the number of particles does not increase or remain same, then the colligative properties also remain same. So I hope it is clear what is basically colligative properties are, right? Any kind of doubt, beta, please ask me. Any doubt related so far, related to this topic so far? No? Shall we proceed? Yeah. Okay. So this is all about the colligative properties. Now, what are the factors affecting the colligative properties are? So there are several factors like fraction of solute and solvent particle in the solution. Okay. Someone text me, sir, this is of class 11. No, beta, this is for class 12th now. This class is especially for class 12th. We are starting with the solution chapter. We already covered 2 or 3 classes of this chapter, right? So this is for 12th. I hope this is clear to you. Right. So what are the factors affecting colligative properties? So the factors affecting the colligative properties are as follow. The first one is that is the fraction of solute and solvent particle in the solution, nature of the nature of the solvent, and extent of association and dissociation of the solute particle in the solution. So these are the factors which generally affect the colligative properties, right? Okay. Now let's move to the next thing. If you understand this colligative properties, then next move to the next thing. There are four colligative properties, and what are the four colligative properties, Arbita? The first one is relative lowering of vapor pressure. The next one is elevation in boiling point, depression in freezing point, and the osmotic pressure. So these four are only the colligative properties we are going to study in our whole course, right? In our this chapter solution. If someone say vapor pressure is a colligative property, you can say no. Vapor pressure is not a colligative property. Only relative lowering of vapor pressure is a colligative properties. On the similar basis, if someone says elevation in boiling point, right? Elevation in boiling point is a uh, colligative properties, but what does about the boiling point only? So boiling point is not a colligative property, because understand here, colligative properties means which depend upon the number of solute. So elevation in boiling point depends whether we add solute or decrease the number of solute, but the boiling point doesn't affected by this, right? So the elevation in boiling point is a colligative properties. On the similar basis, if I'm talking about depression in freezing point, so this is also a colligative property, and osmotic pressure. So these all are the colligative properties, and we are going to study each in a very detailed way, right? So let's start with the first one, that is the relative lowering of vapor pressure, right? So what is relative lowering of vapor pressure, beta? चलो देखते हैं. So we know that according to the Rawls law, the relative loading in the vapor pressure of the dilute solution is equal to the mole fraction of the solid present in the solution. We already studied this thing, right? According to Rawls law, the relative loading in vapor pressure of the dilute solution is equal to the mole fraction of the solute present in the solution. That is, what does it mean, beta? It means P naught minus PB upon P naught. This term is called relative lowering. So this term is called relative lowering in vapor pressure. Remember this, relative lowering in vapor pressure, where P naught is the initial pressure. Now, let me explain with this with the example so that you can understand this thing in a easy way, right? Okay. So let's understand this thing better like this. If I'm talking about the any kind of solution, like if you take some solute, right? If you take some solute and this is your solvent, okay? This is your solvent. Now, if I say vapor pressure of the pure solvent, what do you mean by this term? Vapor pressure of the pure solvent. Vapor pressure of the pure solvent means if we cannot add, it means if we not add any solute on this, then it is known as the vapor pressure of the solvent. So it is represented by P naught. As soon as when we start adding the solute, right? As we start adding the solute, then it will become vapor pressure of the solution. Now it's become vapor pressure of the solution and represented by P. So it is clear now what is P naught and P here, beta. P naught is the vapor pressure of the solvent, or we say pure vapor pressure of the solvent. When, yes,
पूछा ना हमने
yes, beta. Okay. Please mute Priyanka. Right. So if I'm talking about the vapor pressure of the pure solvent, then the vapor pressure of the pure solvent is P naught, and the vapor pressure of the solution is equal to P. So what does P represent, beta? After adding solute, what the vapor pressure become? It is represented by P. And if we want to add any solute, then the pure vapor pressure of the liquid is represented as P naught. So this P naught minus P upon P naught is equal to XV. This is the mole fraction of what? This is the mole fraction of the solute, right? XV means mole fraction of the solute. Is it clear to you? Please tell me. Any doubt related to this? What is relative loading in vapor pressure? Clear है सबको यहाँ तक? Now, so where XB is a mole fraction of the solute, now how will you determine the molecular masses, right? So if n moles of solute be dissolved in n mole of solvent, so we represent moles of solute by small n and moles of solvent by capital N. Then we all know that the mole fraction of solute comes out to be small n upon total number of mole, that is n plus n. So according to the Raoult's law, P naught minus Ps upon P naught, where Ps is the vapor pressure of the solution beta. So this P naught minus Ps upon P naught is equal to n upon n plus n. We can also write n. N is what? That is the number of moles of the solute. So we can write number of moles of solute like mass of the solute upon molar mass. Similar mass of the solute upon molar mass. This is mass of the solvent upon molecular mass of the solvent. So this is how we can write. We know that colligative properties is for very dilute solution, right? We generally use colligative properties for a very dilute solution. So what to do, beta? We know that for dilute solution, a number of solute is very less as compared to the number of solvent, right? Dilute solution means what? If a solvent is present in a larger amount as compared to the solute. So if this n is very much greater than small n, then we can write now P naught minus Ps upon P naught, and this will n plus n. This is n plus n. This will approximately become n only because n is very less, right? So the formula become P naught minus Ps upon P naught into n upon n, and this formula is very important, beta. We use this formula to solve the question. Again, we can write n is the weight mass of the solute upon molecular mass and the mass of the solute upon the molecular mass of the solvent as well. So this expression is used to find the molecular weight of an unknown solute dissolved in a given solvent. So if someone asks, identify which solute is dissolved in this solvent, so we can actually calculate the molar weight of an unknown solute which is dissolved in a given solvent. So this formula is very important, and remember this thing, we use this formula only when the solution is very diluted, right? So this formula is for dilute solutions only, and remember this, P naught minus Ps upon P naught is equal to W into M upon M into W, right? So this is all about the relative lowering of vapor pressure. I hope this is clear to you. Right? Okay. Now, what happened when the solution is not dilute? Right. So this is the fact, when the solution is not dilute, then what you have to do, which formula you have to use. So just remember this, there is an alternate formula for the relative lowering of vapor pressure when the solution is not diluted. So what is the alternate formula, beta? We know that P naught minus Ps upon P naught is equal to Nb upon Na plus Nb. So on reversing this equation, we get, what do we get, beta? Just reverse this equation. So we get P naught upon P naught minus Ps is equal to Na plus Nb upon Nb. Or we say 1 plus Na plus Nb. Now P naught upon P naught minus Ps, this one comes this side, minus 1 is equal to Na upon Nb. So this comes out to be, after solving, we get this, and this is a very important formula, beta. That is P naught minus Ps upon Ps is equal to Nb upon Na. So this formula we use when the solution is not dilute, right? So this formula we use when the solution is not diluted. So this is the important fact here. Here P naught minus Ps upon P naught, and here P naught minus Ps upon Ps, and this is Nb upon Na, right? So this is NB upon NA. So this is all about the fact when the solution is not diluted, right? So this is the alternate formula for the relative lowering of the vapor pressure. I hope this is clear to you, right? Okay, so this is clear to you, okay? Now, the next colligative properties is also very important, that what is elevation in boiling point of the solvent, also known as ebullioscopic. So what do you mean by this term elevation in boiling point? So before study this elevation in boiling point, let's understand, what is boiling point. Can anyone tell me what is boiling point, beta? Anyone? What is boiling point? Okay, let me explain it to you. The boiling point of a liquid may be defined as the temperature at which vapor pressure become equal to the atmospheric pressure. It means if you start heating the liquid, right? If you start heating the liquid, the temperature come at which the vapor pressure of the liquid become exactly equal to the atmospheric pressure, and this point is known as boiling temperature, or we say boiling point, right? So this is all about the boiling point. So boiling point of a liquid may be defined as the temperature at which vapor pressure become equal to the atmospheric pressure, right? I hope this is clear to you. Now, as the vapor pressure of the solution decrease, right? As we know that when you add non-volatile solute, I already discussed in the previous colligative property, that is relative lowering in vapor pressure. As we add non-volatile solute now, their vapor pressure start decreasing. So at this point, we already know that as the vapor pressure of the solution is decreased due to the presence of non-volatile solute, the solution boils at a higher temperature as compared to the pure solvent, right? So this is the fact, because as we start adding the non-volatile solute, the vapor pressure start decreasing. And we know that what is the boiling temperature? The temperature at which the vapor pressure become equal to the atmospheric pressure. Now, if the vapor pressure start decreasing, right? If the vapor pressure start decreasing, what does it mean? It means that you have to boil the solution more to achieve this boiling point, right? So as the vapor pressure of the solution is decreases due to the presence of non-volatile solute, the solution boils at a higher temperature as compared to the pure solvent. Right. Now, the boiling point of the solution is therefore higher than the boiling point of the pure solvent. So as you start adding solute, then the boiling point of the solution increases higher than the boiling point of the pure solvent. And this difference, that is the increase in the boiling point of the solution and actual boiling point of the solvent, is give us elevation in the boiling point, right? So if TB naught is the boiling point of the pure liquid and TB is the boiling point of solution, then what is elevation? Elevation is nothing but it is equal to TB minus TB naught, because TB is the boiling point of the solution and TB naught is the boiling point of pure liquid only, solvent only. So the difference between these two give us the elevation in boiling point. So I hope you get the idea of how elevation in boiling points comes into the picture. Why there is elevation in the boiling point of the solvent. You get an idea, beta? समझ आया सबको? Okay, right. So, how will you find the elevation in boiling point of the solvent, beta? Yes, we can find that elevation in boiling point is nothing but it is equal to delta T, and delta T is equal to TB minus TB naught. The elevation in boiling point is proportional to the molality of the solution or we say this delta TB is directly proportional to molality, or we say this delta TB is equal to Kv into M, right? So this delta TB is equal to Kb into M. So this proportionally constant is Kb, and this Kb is known as ebullioscopic constant or the molar elevation constant. Later we are going to understand this thing, what is Kb here. Let me first explain the graph. How will you get the graph here? And through graph, how will you understand the boiling point elevation, right? So let's understand this thing. This is the vapor pressure along the y-axis, and in the x-axis we are taking temperature. So this point represents the solution. This curve is for solution, and this curve is for solvent we get. So if you draw the, this is the atmospheric pressure. So we know that this point is known as the boiling point, right? This at this temperature only the solution start boiling. The solution start boiling, and this point is known as boiling point, right? This is also known as the boiling point, because in this the vapor pressure of the solution become equal to the atmospheric pressure, and the liquid start boiling. So corresponding to this temperature, we get for solvent we get this TB naught. Similar for the solution, we get this TB. So we know that there is a TB is greater than TB naught. As we see from the graph as well, the value of TB comes out to be greater than TB naught. And this gap is known as delta TB, right? This gap is known as beta delta TB, or we say elevation in boiling point, right? So through graph, you can also understand how elevation boiling point achieves, right? Okay, so here let me explain this term. Kb is known as molar elevation constant. Molar elevation constant. Molar elevation constant, right? So this is known as molar elevation constant, also known as ebullioscopic constant. That is ebullioscopic constant, right? So also known as ebullioscopic constant. What is Kb here? How will you find the unit of Kb beta? We just know from this equation itself, Kb is nothing but is equal to delta Tb upon M, right? So Kb is nothing but delta Tb upon M. So we know that delta Tb, the unit of delta Tb is Kelvin, right? And what is the unit of M beta? The unit of M here is the unit of M. So what is the unit of M here? Unit of M here is nothing but unit of N here is nothing but molality. That is moles per kg, right? So that is mole per kilogram. So we can easily calculate this Kelvin mole per kilogram. So we can find, Kb by using this equation. That is K upon mole per kilogram, right? So this is how we can actually find elevation in boiling. I hope this is clear to you. Yeah. So how will you determine the molecular mass, right? So if you know this, what is molar elevation constant and what is the elevation boiling point, you can easily determine the molecular mass. So it's a very simple thing. We all know that molality is nothing but what mass of the solute upon molecular mass into 1000 upon mass of the solvent. Just put this value. So we know that delta TB is nothing but Kb into molality. So this is Kb and this is the formula for finding molality. So we can find, delta TB by using this formula. So in many questions, you have to find the, boiling point of solution. So to solve this, to do this, what to do beta? First of all, you need to calculate delta TB, right? Once you calculate delta TB, then just put delta TB is equal to what? Delta TB is equal to TB minus TB naught. Just put delta TB is equal to TB minus TB naught. And from this equation, you can easily calculate this, right? So this is all about how will you actually calculate or derive the equation for the elevation in boiling point. So I hope this is clear to you. Any doubt, beta? No? Right. So this is all about the elevation in boiling point. That is, whenever we add some solute, their boiling point increases, and due to this increase, because we in the beginning also we already discussed this thing, that colligative properties depend only on the number of solute. Right. So this property depends only on the number of solute. So as we start adding the non-volatile solute, the boiling point elevation also start rising, and the difference between the a boiling point of the solution and the boiling point, or we say pure boiling point of the liquid, give rise to the elevation in boiling point. And this elevation in boiling point is nothing but it is equal to, or we say proportional to, the molality of the solution. So this delta T is directly proportional to the molality of the solution. And proportionally constant here we use is molar elevation constant, or we say ebuloscopic constant. Right? So this is all about. Now, determination of the molecular masses. So we can easily determine the molecular masses by just putting the values. That is delta Kb is equal to Kb. Just put the formula of molality here. That is mass of the solute. Molecular mass 1000 upon mass of the solvent. These things we already discussed in our previous class. How to find molality, mole fraction and all. So I hope this is clear to you. Anyone beta, any kind of doubt, please ask me. Or is it clear to everyone? सबको क्लियर है, सबको समझ आ गया यहाँ तक? Right? Okay. So as we discussed already now, unit of ebuloscopic constant is Kelvin mole per kilogram, or we say Kelvin kilogram per mole. So we can derive the units of Kb as well. Now, what is freezing point? So this is our this is another important colligative properties. This is the third colligative properties we study. That is, what is depression in freezing point. So before study depression in freezing point, because it is very much similar to the elevation boiling point. Just differentiate here. We are talking about the freezing point here, but in case of elevation boiling point, we are discussing about the boiling point. So can anyone tell me what is freezing point? So freezing point is nothing but it is the temperature at which liquid and solid state of substance have the same vapor pressure. Right. So the freezing point is the temperature at which the liquid and solid states of the substance have the same vapor pressure. This point is called freezing point. Since the vapor pressure of the solvent is lowered by the addition of non-volatile solute, we know that the freezing point of the solution always lower than that of freezing point of the pure solvent. Right? Because we know that the vapor pressure start decreasing. We know that, we know this thing. The vapor pressure start decreasing as soon as we add non-volatile solute. Okay. So in this also, we know that there's what is freezing point. That is the temperature at which the liquid and solid state of the substance have the same vapor pressure. And as we already know, by adding non-volatile solute, their freezing point of the solution is always lower than the freezing point of the pure solvent, because their vapor pressure start decreasing. Right? So understand this thing with the relation of vapor pressure. Okay, so this is all about the depression in the freezing point. Let me show with the example. If I'm talking about, this is a pure liquid, right? So, and now we add some solute, non-volatile solute. Non-volatile solute means what, beta? Anything which is solid, which does not produce any vapor, is known as non-volatile solute. Okay, so if I'm talking about freezing point, so freezing point of pure solvent. Pure solvent means what, beta? Pure solvent means here pure solvent means if you want add any solute, then what is the freezing point? Then the freezing point is represented by Tf naught. Now after adding solute, the freezing point of solution, so freezing point of solution become Tf. Right. So freezing point of pure solvent is equal to Tf naught, and freezing point of the solution is equal to Tf. So what is the depression in freezing point, beta? We know that the freezing point of the solvent or a pure solvent is always more because as we add non-volatile solute, freezing point start decreasing. So it comes out to be TF naught minus TF. Whereas in case of boiling point, it is equal to TB minus TB naught. So this point you must remember better, right? Delta TF is nothing but is equal to TF naught minus TF. So this is all about the depression in freezing point. So here also we find the depression in the freezing point is directly proportional to the molality, and this is known as Kf. So Kf is also known as molar depression constant here. So in the elevation boiling point, it is known as molar elevation constant, where in this it is known as molar. What does it known as, beta? Molar depression constant. So just remember this. This Kf is known as molar depression constant, right? And M is known as molality. So M is known as molality and Kf is known as molar depression constant, or another name of Kf is chiroscopic constant, right? So this is chiroscopic constant, right? So this is also known as chiroscopic constant. So this is all about the depression in freezing point. I hope this is clear to you. Right. Now, how to determine the molecular masses? So on the same basis, just like elevation boiling point, because here also delta TF is directly proportional to molality. Now, so we use the just similar formula of molality and we derive the determine the molecular masses. As we know that molality is nothing but mass of solid, molar mass, 1000 multiplied by mass of the solute upon molar mass, 1000 divided by mass of the solvent. On putting this value in this equation, we get delta TF is equal to this. Or we say molar mass of the solute is comes out to be Kf into W into 1000 upon delta TF into W. Right, where W is the weight of the solute and capital W is the weight of the solvent, M dash is the molecular weight of the solute. So this is how you can calculate the molecular mass of the molecular mass of what? That is the molecular mass of the solute, right? So this is all about the depression in freezing point. Unit of Kf is also remain same, that is Kelvin kilogram per mole, and we can easily calculate this. So the molar depression constant Kf can be calculated from the molar heat of fusion of solvent using this expression as well. So try to learn this expression also. In some cases, questions were coming directly from this topic alone. That is, this is M into R into TF square upon delta H of fusion into 1000, where M is the molar mass, TF is the boiling point of the solvent, and R is nothing but the gas constant. So this is all about the depression in freezing point. So in today's class, we are discussing about the colligative properties, understanding what is colligative properties with example, and also discuss three very important colligative properties, that is relative loading in vapor pressure, elevation in boiling point, and depression in freezing point, right? So in our next class, that is on Friday, we are going to discuss about the one remaining colligative properties and the numerical based upon these colligative properties. Okay, so this is all for today class. Let's meet in the next class and discussing remaining one colligative properties, right? So till take care and just revise the concept. Okay.